What if I told you that there was an operation in math that only exists in 3D space and 7D space? Now, at first, intuition might make this seem odd. How could an operation only be defined in these two spaces so remote and dissimilar from one another? But after perusing the Math Stack Exchange and consulting my good friend Rand Polnitz, I finally learned enough to yap about this for like 8 minutes or whatever. So, why should anybody care about this operation? Especially if it only works in 3 and 7D space. It sounds way too esoteric or vexed or vector multiplication. Take your two favorite orthogonal vectors, and what cross product will do is find a specific third vector that's orthogonal to both of those vectors. Now, to some of you it might seem odd, in dimensions higher than 3D space, isn't there an infinite amount of vectors that satisfy this criteria? And it's true. Even in 3D space, the case is the same. So how does cross product actually work? Okay, maybe the operation's doing a little bit more than what I said it did previously. So let's do a quick example with the two vectors v1 and v2 multiplied together by cross product. Geometrically, what's happening is there's an area being constructed by the parallelogram bounded by these two vectors. Then we set this area to the magnitude of the output vector, v3. This area is called a determinant, and this determinant is, in this case, 6. This eliminates most options from the infinite line of possible orthogonal vectors, but still there's two vectors that have a magnitude of 6 and are orthogonal to the first two vectors. There's 0, 6, 0 and 0, negative 6, 0. So how do we know which one's the right answer? Take your right hand and point your index finger in the direction of the vector on the left of the multiplication sign. Then take your middle finger and point it in the direction of the vector on the right hand of the multiplication side. Your thumb will then point to which one of the two vectors left is the correct vector. Notice the non-commutativity of this operation. If I were to switch the vectors, I would get a thumb pointing the other way.
We can understand cross product as an operation that takes all vectors in a dimension and then eliminates them according to a specific set of rules to output a singular vector. This allows us to see why it breaks down in higher dimensions, as the orthogonality elimination leaves vectors that lie in more than one dimension. In 4D, a plane of vectors is left. In 5D, a hyperplane. So, why does cross product work in 7D? Okay, let's take a step back. Cross product can't always be visualized this easy. What if the vectors don't lie on any axis? Do computers have to draw these silly little pictures every time they want to compute? What I'm asking is, what's the math for this? Let's take vector 1 and vector 2, both of which are orthogonal and do not lie on any of the axes. Let's split them apart as expressions of vector addition, where a scalar is multiplied by a unit vector. Let's represent these unit vectors as I, j, and k. We can form a square matrix with both vector 1 and vector 2, then put I, j, k as placeholders up top. Finding the determinant of this matrix gives us negative 5i plus 4j minus k, which is the same as the vector minus 5, 4, and minus 1. All great stuff, but why are the unit vectors called I, j, and k? We know that the square root of negative 1 is equal to I, a poorly named imaginary number, meaning 1 times I is I times I is negative 1, and negative 1 times I is negative I. But what does this look like geometrically? Well, we take two axes, the real number line and the equally poorly named imaginary number line, and we form a plane with them. Any expression involving these two numbers, let's say 3 plus 2i, can be plotted on this plane. We see that multiplying by I transforms this point to 3i minus 2, and multiplying again leaves us negative 3 minus 2i.
Golly! It seems like these are just rotations around the origin. To be precise, orthogonal rotations around the origin. And to be double precise, clockwise orthogonal rotations around the origin. But what if we double the dimensions? Let's add two more dimensions, j and k. These letters should look pretty familiar by now. And with these two additions, we've turned a simple complex plane into a quaternionic space. 4D is similar to 2D in a lot of ways. For example, both spaces stay true to the associative property, and in both spaces, I times I equals -1. And both spaces treat a multiplication of I as a clockwise orthogonal rotation that keeps the norm. But it's this keeping of the norm that leads to our first difference, as in order to keep this norm, we must make our first sacrifice. Commutativity. Take an arm, any arm, and what we're going to do is apply a series of rotations to it. The first rotation will be about the z-axis, then about the x-axis. Remember this ending position. Then we're going to restart back to the starting position and switch the order of those two rotations. So first above the x-axis and then about the z-axis. We can see these ending positions are very different from each other, despite applying the same two rotations. We can see that the commutative property doesn't hold in any dimension above 2. So now, in quaternionic space, a bunch of rules are added, with any swapping of the rules leading to a negative output, because, once again, there is no commutative property here. When performing cross product, we've been using this quaternionic system, representing 3D as a pure quaternion, or a quaternion with 0 real counterpart. It's kind of like we're projecting 4D into 3D space. To better picture this, let's imagine we're projecting a plane, a 2D space, onto a line, a 1D space. First, we could take a unit circle in the complex plane and try to project it onto the vertical axis. The way we do this is we take the point -1 plus 0i, and we send a bunch of lines out that intersect with every single point on this unit circle. Now, there should be a 1-to-1 mapping of this line that intersects with every single point on the vertical axis and the unit circle, with the point itself being projected into the positive and negative infinities. We can see from a lower dimensional point of view that every time the circle rotates, it appears as though there's a translation along this vertical axis, albeit a non-linear translation. So let's take a look at what this hypersphere projection looks like in 3D space.
Here appears to be a sphere, but do not be fooled. It is simply a projection of a higher dimensional sphere onto 3D space. Watch as I left multiply the position of this sphere by I. We can see that the circle rotates around the I-axis 90 degrees, with j moving to k moving to -j moving to -k, and -k moving to j, in accordance with the rules defined previously. It seems like there's also a translation along the I-axis, but remember, sometimes a rotation might appear like a translation when projected onto a lower dimension. In actuality, we're witnessing a hypersphere rotate. Reset, and instead, right multiply the position of the sphere by I. Notice the non-commutativity of the quaternions in front of you. The sphere appears to translate along the I-axis, the same way as before, but the rotation along the I-axis reverses. If you play around with this on paper, you might get a better understanding. Okay, let's double the dimensions again. Adding 4 more letters feels terrible, so let's change them all into E and then a subscript with the real counterpart being E0. But wait, before any math can be done, another sacrifice must be made. The way that quaternions gave up commutativity, the octonions must give up associativity to keep the norm. From this set of restrictions, even more rules are added. Okay, so there's like 7 triads that exist in octonion algebra, and what these are is extra multiplication rules in higher than 4D space. We're actually already familiar with one triad, being I, J, and K, or E1, E2, and E3 respectively. That's all a triad is, a bunch of quaternionic triples in octonionic space. The rest are 145, 176, 246, 257, 347, and if you think the first 2 numbers add to the third, you receive a soul-crushing 356, because the number ascribed to these octonions don't matter. They're just names. Okay, let's do some cross product.
Let's take 2 vectors in 7-dimensional space and obviously cross multiply them with each other. We can see that vector 1 is equal to E5 and that vector 2 is equal to E1. We can use one of the triads to figure out the cross product between these 2 vectors, and we get E4 which is equal to 0, 0, 0, 1, 0, 0, 0. Now, let's do a harder vector cross product. Okay, let's take two more vectors, and then represent them as an addition of scaled unit vectors. And then let's multiply these vectors together, making sure to keep associativity. After distributing, we can see that we've reduced the cross product of these two vectors into a string of the simplest octonion cross products. We can then use the triad rules to simplify this down further and get our final vector.